Okay, so we will now discuss vapor liquid equilibrium, and let's start with VLE phase diagrams. So VLE phase diagrams, and let me emphasize that I am currently considering only the PV projection. I will discuss in detail why do I refer to this as a PV projection. But before we actually try to understand in greater details about the vapor liquid equilibrium and its phase diagram, let's first try to remember our van der Waals equation of state. So van der Waals equation of state, and that was P plus A n squared by V squared V minus NB equals nRT. Okay, and we have already discussed in class what is the significance of this correction to pressure term, the significance of correction to volume term. But let me try to make this expression expressed in terms of powers of volume. So what I can do is I can multiply the whole expression by V squared, so it will be P V squared plus A n squared V minus NB equals nRT V squared, and I can further simplify this as PV cube minus PNB V squared plus A n squared V minus A n cube B minus nRT V squared equals 0, and this can be rearranged as P V cube minus Pn plus nRT times V squared plus A n squared V minus A n cube B equals 0. Now, so this is an equation of state in which we have expressed the relationship between P, V, N and T such that we have the coefficients multiplied by powers of volume. Okay, and therefore this equation is of the form alpha V cube plus beta V squared plus gamma V plus delta equals 0, which is a polynomial in V cube. Okay, so obviously when we solve this, what we will get is three solutions of volume. And what does that mean? And that means that we can have three volumes for a given P and T. Now that's strange because if you are given a set of pressure and temperature, then you would expect a unique volume. And say, for example, if you follow the ideal gas equation, PV equals nRT, so I can always write this as V equals nRT by P, following which, if you know T and if you know P, you know that there exists only one value of volume. But our van der Waals equation of state is cubic in volume, which means that you should have three volumes, right? But we have already discussed this in the class that if you actually plot this PV for real gas, what you will observe is something like this. Okay, so now what I can do is I can so this This curve is an isotherm, so it is at a given temperature, and what I get is one value of V here, another value of V here, and third value of V here. And what we discussed is that this one is the volume of a liquid, volume of the liquid phase. This one is the volume of the vapor phase. The question remained was, what is this? Does this exist? Does this exist? And I had said that you can either have these two volumes, or as you increase the temperature you will come across a situation in which you have only one volume. All these three volumes become equal, and later on you get only one volume. But this is non-existent. This is non-existent, the intermediate volume. And what is the reason? Why does this happen? To understand this, we'll have to resort to the vapor liquid phase equilibrium, and we will develop this VLE PV projection on the basis of stability criterion. We have already discussed that several stability criteria exist, but what we will do is we will choose one particular criterion of interest and try to understand and develop the phase diagram on the basis of that. Okay, so one of the stability criteria can be this del squared A by del V squared at constant T and N. Now since A is a thermodynamic potential, this has to be minimum. This has to be minimum, and for that this must be greater than 0. This is our stability criterion. Okay, so now what information can I extract from this? To extract information from this, let me use this. Let me say that I can write this as del A by del T by del V, sorry, at Tn del by del V at T n, and this has to be greater than 0. But what is this quantity? What is this quantity? Del A by del V at constant T and N. What is this? So we know that dA equals minus of SDT minus of PdV plus summation I equals 1 to capital N for an n component system mu I dni. Here we have pure gas, so we have I is just 1. So from here we get del A by del V at constant temperature as negative of P. Okay, so from where we can write that del by del V of minus of P at constant temperature and number of moles must be greater than 0. So what is our working stability criterion? Working stability criterion. A working stability criterion will be del P by del V at constant T and N must be less than 0. Okay, this is the stability criterion. So if the system has to be at stable equilibrium, del P by del V at constant T and N must be less than 0, and this is actually called the criterion for mechanical stability of the system. Mechanical stability. And if we try to understand what exactly does this criterion mean, this simply means that at a given temperature, and if you fix the number of moles of the system, that means you're not adding any mass, you're not taking any mass away from the system. If you try to increase the pressure of the system, the volume will decrease, or if you try to increase the volume of the system, the pressure must decrease. So So this is it is also very intuitive if I try to understand. So if I have a block, and what I do is I pressurize this. So pressure increases. What is going to happen is this whole block will squeeze. So as pressure increases, volume should decrease. So therefore, this gradient del P by del V at constant T and N must be negative. And this is a very important criterion, and we will develop the entire VLE phase diagram on the basis of this criterion. So let's see how can we use this criterion for developing the phase diagram. So all I know at this point of time from this phase diagram is the variation of pressure with volume at a given temperature. So let me take P and V as the coordinates. I don't know anything else about the system, but what I do know is that if the system is a multi-phase system, then two phases, liquid and vapor, okay, they will have same pressure and same temperature. See these two, at these 2 points the pressure and temperature of the system are equal. So therefore these two, the system is at equilibrium at these 2 points. And if I correspondingly see what are the volumes, this is a volume V, which is smaller compared to let me say this is as VL, which is smaller to VV. So here VL stands for volume of liquid, VV stands for the volume of vapor. And this is quite obvious that if the system is at equilibrium, you have a vapor liquid system, the volume of the liquid will be lesser compared to the volume of the vapor. So at this point the system is a liquid, at this point the system is vapor. They have exactly the same temperature and the same pressure. Okay, but now what was our stability criterion? Our stability criterion was del P by del V at constant T and N must be less than 0. Okay, so therefore what I say is at these 2 points the system is at equilibrium, but if I deviate the system from this, then what should happen? This slope is negative, so therefore what will happen is I can have the system where I can go on reducing the pressure, the volume will increase till I reach this point, and at this point the system becomes in equilibrium with the vapor, and I can again increase the or decrease the pressure, and the volume will further increase. So this is what is going to happen. It's that if you have the system and you decrease its pressure, the volume will decrease. Similarly, for a vapor or for a gas, increase in the pressure will result in decrease in volume, and the other way around. But let us see the slopes of these two. This slope is larger compared to the slope in the vapor phase. The slope of liquid is larger than the slope of the vapor, and this is quite obvious. The change in volume with change in pressure for liquid system is very less compared to the change in volume with change in pressure of the vapor. That's why these two slopes will be different. Okay, so now we understand how do we get these two curves. Now what I do is, so this is at a given t, I say t equals t1. Okay, but now what I do is, since I am following the stability criterion here and the system is stable, so here my del P by del V at constant T and N is less than 0. Here del P by del V at constant T and N is less than 0, and the system is stable. Okay, but what I can do is I can continue this particular curve such that I reach a point, and at this particular point, my del P by del V at constant T and N becomes 0. Similarly, I can continue this till I reach a point such that at this point my del P by del V constant T and N becomes 0. Okay. Now see, the system already had reached equilibrium, so these are at equilibrium and equilibrium. The system already had reached equilibrium at these 2 points. So therefore, the moment you reach here and you make any deviation, the system will tend to jump from here to here. The system will tend to jump from here to here. You will not observe this intermediate. You will not observe this intermediate stage. Okay, but let me say that I do this process of taking the system from here till here very carefully, in very small, by making very small differential changes in the properties of the system. And what happens here actually, when I am here, what happens to the stability criterion? Here also del P by del V Tp is less than 0. That holds, and this is also the case here. So along this orange curve, the system is actually stable. Okay, it's not, and I don't know whether it's stable or not, but I can what I can say for sure is that it's not violating any stability criterion, right? So I can actually extend. But what happens at this point? The slopes become 0. Here the slope becomes 0. Okay, but then I go on expanding my liquid, I go on compressing my vapor. So what I can do is I can come up with a curve which joins this, or let me make it a bit better. I can come up with the curve such that I can join these two. Okay, but what happens to the stability criterion here? Here del P by del V is greater than 0. It's greater than 0. So this particular portion, so the system is unstable in the portion which is shown in red. Okay, but now let me very carefully try to analyze this curve, and let us compare this curve with this particular curve, this one. What I observe is I see the same trend. So let me see. So what I can do is I say that I have a PV projection. And I get a curve like this. This is what we developed just now. Okay, and what happens is that when I take a horizontal line, and I look at these two volumes, I find that this is VL, volume of liquid, this is VV, volume of vapor, but this one actually falls within the unstable region. Therefore, this volume will never be observed. It will never be observed. Therefore, you have V lower, V liquid, V higher, or V vapor, and the intermediate volume will never be observed. So now I move further and I change the temperature of my system. So at a given temperature, what I had was, I have P, I have V, okay, and I chose 2 points. I chose 2 points here, those are the two equilibrium points, and what I get is a curve like this, okay. And then I said that I can continue till the slope becomes 0, can continue from here till the slope becomes 0, okay. I get these 2 points, okay, and then what I mark in red is the unstable region, okay. So now I can mark this, this is the equilibrium saturation, so is this point equilibrium saturation, okay. And I drop these 2 points here, and I get VL and I get VV, and this was at a given temperature. Now I increase the temperature, but as I increase the temperature, what will happen is these 2 points will come closer, okay, and the behavior of the system beyond this must continue, right. And similarly here you will have where the system becomes just becomes attain the limit of stability, and here you have unstable region. What if so here I have T2 and T2 greater than T1, okay. What if I increase the temperature further? If I increase the temperature further, what's going to happen is these 2 points are going to come even closer, and so on. So what I do is I take the locus of all these points. See these all these saturation points. I take the locus of all of these, okay, and I join them. So what I do is I take the locus and I join, and what's going to happen is the difference in the volume is decreasing. So therefore I might reach a situation where the difference in the volumes actually becomes 0, okay. And then the drawing is not very elegant, but ideally what you will observe is a curve which looks something like this. If I draw it very properly, the curve will look something like this, okay. And this curve is called equilibrium coexistence curve, and the system is at equilibrium along this curve called the equilibrium coexistence curve, okay. Now what happens if I go beyond this? So in this region, everywhere. So by which I mean anywhere here, okay. What happens in this region? So in this region, if you see del P by del V less than 0 here, similarly del P by del V is less than 0 here, which means that the system is stable. So therefore in this region the system is stable. Everywhere the system is stable, okay. So all of these places, whichever you take, the system is going to be stable. You are going to observe the system. Okay. But then what I can do is I can take the locus of these points where the slope has just become 0. The slope has just become 0. Okay. So this is the locus of the points where del P by del V Tn has become 0, and this is called limit of stability. Okay, and it turns out that if I join this using all of these points, it terminates exactly at the same point and it comes back. So if I draw it in an elegant manner, it will look something like this. Okay, so let me draw it in a better way, in a larger manner. So you had okay, and you set this as the equilibrium coexistence curve, and the system was stable. It was stable everywhere here. Wherever you go, the system is stable. And the system is stable for a simple reason, that del P by del N at constant Tn was less than 0 everywhere, wherever you go in this region. But then what we said there is that we can also draw the locus of the points where del P by del N is 0. Del P by del N is 0. So this is for this curve. Okay, then you can have del P by del N, this curve and beyond, del P by del N at T and N equals 0, which happens to be this curve. Okay, and this curve is called, okay, by the way, the equilibrium coexistence curve is also called the binodal curve, and this curve is called the spinodal curve. Okay, and what happens actually now here in this region, del P by del N at constant T and N is greater than 0. So system is unstable. The system is unstable in this region. You cannot observe the system. But then the question is, what happens in between? So in between, which is this region. In between is this region. So the region between the binodal curve and the spinodal curve. So the system is metastable in this region. Okay, so if we go back, you will see that between these, so this is the region where the system is metastable. The system is stable elsewhere, and here in this region the system is unstable. So we'll see the implications of metastability on various chemical processes in a later section. But what we learn from this particular phase diagram is that there exists 3 regions: stable region, metastable region, and unstable region. In unstable region, the material does not satisfy the stability criterion, as a result of which there is no process by which we can observe the system to be in such a state. By all processes, you can always observe the system in stable state, but if you want to go beyond the stable state and access the metastable region, then you have to carry out the process really very carefully, because the moment you introduce some amount of I would say large amount of fluctuation in your system, the system is quickly going to undergo a phase change.